Assalamualaikum and good day everyone. So we will start with a week 10 lecture, okay, with encoders. Okay, now let me see where are we right now. Okay, if you guys see, we are in the current week 10. Okay, in week 10 we are expected to learn about encoders, concept, device, 74 times 148 expansion, and so on. And then we will learn about adders, which consists of half adder, full adder, ripple adder, device, and comparator device. Okay, if you guys notice, when I'm lecturing, my teaching method is mixed. Either it's coming from the slide or it's coming from the module. Okay, if I teach from the module, I will still share the slide, and if I teach from the slide, you guys still able to learn whatever being taught in the module by reading the module and by doing the exercise. So that's why if you guys notice, I keep on asking you guys to do the exercise of the module, because sometimes when I lecturing from the slide, okay, then it, it needs some more complement from the module. Okay, how to do this? You said you try to do the module exercise. Okay, likewise, if I teach from the module, there must be something that maybe that the module cover but not complete, then it will be covered by the slide. Okay, means to complete, you guys need to have both information from the slide, from the module. Okay, and of course by doing exercise as well. Okay, so before further ado, we will start this lecture with week 10 encoders. Okay, so encoders, before this we already studied about, we have learned about decoders. Okay, now we go to the exact opposite, which is the encoder. Okay, so encoder, the overview. Encoder perform reverse function of decoder. Okay, by the name itself you already can see you perform reverse function, just like how demultiplexer perform reverse function of multiplexer. Okay, so likewise for encoder, it perform reverse function of decoder. Okay, encoder used to compress the input into a code that contains the same information in fewer bits. Okay, what we do in encoder is actually we compress the input, okay, into a code that contains the same information, however in fewer bits. Let's say you have inputs, means that for this encoder you will have many inputs and you will have less input, okay, and less output. From many input to the less output, so it will has a 2n input and n output. For example, if you have four input, for example, means you have 2 to the power of 2, am I correct, input. So how much your output will be? Your output will be 2 output only, okay, following this convention. Okay, 2n to n connection. Only one input is allowed to be active at any one time. Only one input is active at any one time. And as you guys have learned from the previous lecture about these chips or circuits, we have active low or active high. So you need to make sure which one it is referring to. Let's say if we have a chip with a bubble, means the one active is the active low. If we have like this, just normal, means the active is high. So active high input or active low input, you need to know the differentiation. Okay, simply by just looking at the bubble. So if for these encoders, only one input is allowed to be active. However, sometimes maybe there will be one or more input active. So that's why this one will require different types of encoder, which is the priority encoder. Okay. Now we go to the 4 to 2 encoders. Okay. 4 to 2 encoders consist of 4 inputs and 2 outputs, just like 2 to the power of 2, and this 2 will be the number of outputs. Okay. So the function is that, let's say we have A0 and A1 as the input, as the output, and then you have this one connection to the connection to the input is D0, D1, D2, D3, and you can set, like for example, you can set here O3 until O0. Okay, and if you can see, this one is the active flow input, means it is active if you only give it input of 0. Okay, to activate. Okay, because this one is the inverted input. Okay, so let's say the function to have A1 and A0 is to be output of 0. Okay, then the combinational input expected is here A3, A2, S1 with the active one at 0, output at O0. Okay, if you want the output to be 1, 1, it must have combinational inputs of 0, 1, 1, with O3 is the active load. Okay, so it's simple like that. So when you do a function table, you obtain a diagonal pattern like this. Okay, this is an active low input. Okay, then by having like this as your 0, 0 at O, you will have output as 0, 0. If you have 0, 1, if you have 0, O1 as 0, you will have combinational output of 0, 1. Okay, by seeing this table, then you construct an expression for A1, for example, for the whatever minterm or maxterm. So let's say this one, you take the function which output function which result to 1, you will not obtain that. For A1, you will have D3, D2, D1, D0, D3, D2, D1, D0. So you can see this is the function. This one is correspond to the D2, and this one is correspond to D3. Okay, so don't confuse. Okay, this one O3 means the combinational input, and D0 until D3 is actually the input pin. Okay, the input pin. So what happens if more than one input 0 is observed? What happens if we have, for example, okay, let's see first our combinational input. Okay, what happens if we have this kind of combinational inputs? Okay, here. So what happens if we have 1, 1, 0, 0, which actually the same as D0, 1 and D1, 0. Okay, because as we see from the previous slide, only one active input is allowed at any time. So what happens if we have more than one input active at a time? So that's why here where we need a priority encoder. Priority encoder will help us to choose either one of the more than one existing inputs to be translated at our output. Only one means the rest will be ignored regardless what input that we will have, either 1 or 0. Okay, it will take the priority. Okay, the priority one. So how is the priority encoder operates? Okay, the next slide is priority encoders. Okay, priority encoders is the output depends on largest active input. It depends on the largest active input. Means it depends on the we can simply say is the most significant bit. Okay, for example, so for easy understanding, okay, it can be referred as the most significant bit for the active inputs. Okay, so for example, let me go for the first combination. Okay, if we have A3, A2, A1, 0, we have 1, 1, 0. Okay, this one is active low input. So here we have no problem because we only have one active input, which is at all 0. Then the output will surely as 0, 0. Okay, next, imagine that we have the next combinational inputs of 1, 1, 0 and don't care. What does it mean by don't care? Because even if we have, okay, 1 or 0, it will not be considered. Okay, it will still refer to this as the next priority, is the as the first priority. So if you have 1 here, no problem, it will still be coming like this as the output. However, what if you have 1, 1, 0, 0? When this happens, it will choose this. Okay, the most significant active input. Okay, so this one will be treated as the least priority. So that's why in this position, it is don't care whether it is 1 or it's 0. Likewise, for the third combination inputs, okay, we put this as our priority. Then this will be these two less significant or less active input will be treated as the don't care conditions. So regardless of what 0 or 1 the value they may have, our output still 1, 0. Okay. Finally, likewise, the fourth combinational inputs, regardless of what combinational inputs that you have here, okay, either 0 or 1, if this will be set as the main priority, the first priority, so it will still be output of 1, 1. Okay, please take note that from the in the previous slide, okay, this one is active low output, the same as this one is active low output. So you need to be careful in deriving your output results. Okay, if it's active low output, then it is inverse, okay, contra. So the function table for the priority encoders, okay, imagine that now you can see, right, when you have 1, 1, 0, it is just as normal, and when you start you have 0 in the diagonal pattern like this, okay, you will ignore the state of the least significant bits input. Can be understand like that, okay, can be treated like that, because this word is a bit not really easy to understand, so I just use significant or less significant for your understanding. Okay, so we can see as this diagonal pattern is increasing in the more significant bits, this one will be ignored. Okay, and least significant input will be ignored. So this is the corresponding. So then you will have this is as your output of 1 for A1, and this one is the output of 1 for the A0. Okay, so question here, what happens if more than one input is 0? Then like for example D0, D1, D0, D1, then it will still choose this one, okay, regardless of whatever OO we have. OO is a connection to the D0 pin. Okay, this is the input pin D, but this is our input assignation. So according to the syllabus, okay, we'll go about 74.71 chip as well. So this one we will cover in the class by referring to the module, and of course, because you guys have done the exercise, I expect that you guys have some a bit knowledge about this. Okay, so it's good. Do exercise, listen to lecture, and read the slide and read the module. So inshallah, I think you will do just fine. And of course, you guys need to do some exercise on the past test and also past final. Okay, we will cover B7 to BCD to 7 segment display decoder already indirectly from your exercise, right? Module exercise. Okay, but I will cover as well because it is application of these decoders. Okay, that we already covered in the previous lecture. Okay, so BCD to 7-segment decoders. What does it mean by BCD? Just like I told you guys, BCD is the binary coded of the decimal numbers. Mean decimal number that we have is 0 until 9. You couldn't have 10 until 15. That is impossible. The decimal numbers is from 0 until 9. That's why we call it binary coded decimal. It's just a decimal number represented in binary number. So to 7-segment decoders. Okay. BCD to 7-segment decoders accept BCD codes on its input and provide output to drive 7-segment display to produce decimal readout. This one is actually the conventional display, like maybe you may have this in calculators. Okay, the digits, the numbers. Logic symbol for BCD to 7-segment decoder with active low output. Okay, here. This one is quite straightforward. That's why I believe that you guys still can do it. Okay, after having go through the lecture slide of decoder general slide about decoders. Okay, so logic symbol for BCD to disable decoder with active low outputs. Okay, so this is your BCD input: A0, A1, A2, A3. And this is your A, B, C, D, E, F, G. This is actually the locations of your display. Okay, display. So two types of 7-segment display. You can have common anode and common cathode. So by the name itself, you already know that common anode is a connection where the common, okay, where source voltage source, okay, the anode is being common to all of the display. You can see here, right? Everything is connected commonly with the anode. Okay. Likewise for the common cathode. Okay. For common anode, LED on when low input applied. Common cathode, LED on when high input is applied. Okay, you guys already have this slide. Okay, I given earlier. Okay, it is given in the previous weeks. Okay, because this slide have 73 pages, 73 slides, 73 pages, whatever you call it, and so you guys already have this information. Okay, so please please read all the slides, all the module, the exercise, to past years, and so on. Okay, and for you to get through this subject successfully. Okay, so common cathode is LED will on when high input is applied. Okay, what does it mean by this? Okay, so if you see here, common anode LED is on. Okay, LED is on. However, we need to connect it to the low input. Here is the low input. Okay, for example, okay, for it to be on, we need to put all this connection to low. Okay, means that when this one is low, you will have positive to negative connection complete. Then this one will turn on display. Likewise for the common cathode. Okay, if you see for common cathode, you can see everything is being connection to to the ground. Okay, sorry, I reduced a bit this display because the bar is disturbing our view. So too small, wait for a while. Okay, so the same for the common cathode. Okay, it will connect to all the ground. The ground here will be the cathode. Okay, means less positive. Okay, so in order for this to be turned on, we need to put a high input. For example, here, in order for this to turn on. Okay, that's why LED on when high input is applied. Okay, BCD to 7-segment decoders. Okay, overview. Okay, the 74 times 44 is an example of IC device that decode a BCD input and drive a 7-segment display. Okay, the 74 times 47 is a common and net display. Okay, so I think from you start to have this kind of numbers of chip. Okay, and so in some way I hope you guys able to do some memorization a bit. Okay, about these chips numbers. Okay, and what the characteristic they have. However, if you don't really able to memorize all, okay, if the question give you this kind of connection or this logic symbol, I believe that you guys still able to do. Okay, because as long as you know what is this pin, what is this ground function, what is this RBO function. Okay, for this detailed explanation, you should refer to the module. Okay, so this is a connection diagram for the 74 times 47 IC DI in package, dual inline package. So sometimes we refer this as DIP. Okay, this one is actually to show our position of counting, and this one is showing that the your pin number counting is arrangement from here. Okay, from following this counterclockwise. So the logic symbol that we may have. Okay, so we convert 4-bit BCD A3, A2, A1, A0 to 7-segment LED, which is A, B, C, D, E, F, G, H. Okay, sorry, anti-G. So you can see A, B, C, D, E, F, G, and H. Okay, you can see it is in the clockwise manner, and this is sometimes we have input for to as DP output. Okay, we have input to make an DP output. This DP is actually the decimal point. Okay, so each of these pin is I believe it is explained quite detailed in the module. Okay, yes, it's explained quite detailed in the module, so please refer to module for your understanding to read it. Okay, and if you guys don't understand, feel free to ask me. Okay, about this. Okay, so we go to the next slide. Okay, so this is decimal value. For example, if you want to have a decimal value this as your output, then your BCD code is this is your corresponding BCD code. Okay, and what display will be turned on and what will display will be turned off. Okay, this is the corresponding. I think this one is quite straightforward and easy to understand. Okay, inshallah. Okay, so if you have, let's say for example, if you want to have a decimal value of 0, means it will light what? It will turn on all of this A, B, C, D, E, F, turn on, and G will turn off in order for it to display a digit of 0. Okay, what happened to G? G is turned off. Okay, if you guys can see here, they are active low. Okay, they are active low output. Okay, they are active low output. So you see the bar here, then you know that each those that with 1, they are not active. So means they are not displaying because we have active low output. Okay, we have active low output display. You can see here, right, with the bar function. Okay, so those that having 0 will be turned on. Okay, here means A, B, C, D, E, F is turned on. Okay, the same concept goes along all the way until 9. You can test yourself. Okay, so for your more understanding. Okay, so 7-segment common AND display 74 times 74. Okay, so this you can see it is an active low output. Okay, so adders and comparator will be covered in next lecture. Okay, this one I will using for adders I will be using module exercise. Okay, inshallah. So see you in the next lecture. Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera.